Bismillahirrahmanirrahim. ELE424 Analog Electronics 1 Metal Oxide Semiconductor Field Effect Transistor. We are now ready to do AC analysis. We have completed DC analysis, but now we will be doing MOSFET AC analysis. I am Wan Fazlida Hanim Abdullah. I am from the Faculty of Electrical Engineering, UiTM, Shah Alam. Alright, so the topics that we will cover in set 3, MOSFET AC analysis. As usual, we'll start a little bit with introduction so that we have some sense of appreciation of what's going on. And then we'll look into load lines and small signal parameters. This small signal parameter will be used in the MOSFET small signal AC analysis. And there are many MOSFET configurations, just as there are many MOSFET circuits that can be constructed, but for the purpose of this course we will only look at common source amplifiers. Introduction. MOSFETs in linear amplifier. We will now focus on the use of the MOSFETs in linear amplifier applications. Okay, not because that the other applications are less important. There are even more widely used applications, but because this is Analog Electronics 1, the syllabus is for linear amplifier applications. So linear amplifiers imply that for the most part we are dealing with analog signals that may vary continuously with respect to time. So a linear amplifier magnifies an input signal and produces an output signal whose magnitude is larger and directly proportional to the input signal. Okay, so it amplifies. That's the whole reason why it's called an amplifier, and it is linear, which means that the output form and the input signal are directly proportional. Although a major use of MOSFETs is in the digital applications, okay, they are also used in linear amplifier circuits. Okay, just a little bit more on linear amplification. When symmetrical sinusoidal signals are applied to the input of an amplifier, the magnified output that we said earlier just now that should be directly proportional to the input, it will be directly proportional as long as the amplifier operation remains within the expected region. So distortion is avoided in linear amplification. So we know that if an amplifier system takes in an input signal, it will amplify it. Now, we want to avoid distortion, and this is an example of a distortion, of amplitude distortion due to clipping. So this is what happens. We put in an input signal, we expect an amplified output signal, but somewhere along the line it gets clipped because outside this boundaries, the transistors may be operating in a region that it is not supposed to function. Not supposed to operate. So I got this picture of electronics tutorials. You may want to have a look at that website. So load lines and small signal parameters. We're going to look at more on load lines. I think we left MOSFET DC analysis at load lines, but we're going to look at load lines first, and then we will be introduced to small signal parameters. Now this section won't be actually tested, I think, but understanding of linear amplification and the background overview, if you understand that, it will strengthen the understanding of basic concepts as a whole. So this is a common circuit and common source circuit. So this shows an NMOS common source circuit with an AC source in series with a DC source. So this DC source is labeled with this capital letter and capital letter in the letter itself, and in the subscript as well. So this is VGSQ in series with an AC source, which are in small letters Vin. Okay, so let's assume that this AC signal is sinusoidal. A real signal will not be sinusoidal, but for our analysis we will use sinusoidal signals to represent general time varying signals usually. Okay, so this is a load line, and this shows a Q point from this transistor. How do we get that load line? We get it from, just like BJT, okay, in this MOSFET circuit, we get it from the KVL of the output loop. So this shows the transistor characteristics. This is this family of output characteristics of ID versus VDS curve. It shows the DC load line, which is this solid line in pink, and it shows a Q point a Q point is the intended point of operation, which we will design what VGSQ should be so that it intercepts on the load line for the ID and VDSQ. So this DC load line has an Q point. Here are functions of VGS, VDD, and RD. So for this particular circuit, what controls what the Q point and the DC load line is VGS, VDD, and RD. Because Vin will be this Vin here, this is the input signal. So for the output voltage to be a linear function of the input voltage, because we said it's supposed to be linear amplifier, right? The transistor must be biased in the saturation region. Okay, this region here. It must be biased in the saturation region of the drain current. Can we operate it in the triode region? Yes, we can, and sometimes we need it to be in the triode region for other applications, but for linear amplifier, for ELE424, we want the transistors to operate in saturation region. The DC biasing will ensure if Q point will be in the saturation region here or non-saturation region, which is before this boundary line here. So load line with AC signal. Let's consider the load line with sinusoidal variations. The same thing here with sinusoidal variations in VGS, okay, ID, and VDS as a result of the sinusoidal source Vin. So when Vin changes, can we expect to see VGS changing because it's the same node here? Okay, it will go up and down in terms of value. And if that changes, because VGS fixes ID, especially in saturation, okay, so we'll expect some changes there as well, and VDSQ. Alright, so we have the same load line. We're still looking at load lines, but now let's just imagine that VGS is now varying. With Vin here, okay, VGS is a combination of DC and AC components. VGS is a combination of DC, this is DC, which is this DC source, and and AC, which is this input voltage AC source. So what's going to happen? Now as Vin increases, because it's varying with time, right? So just like sinusoidal, it will first increase and then it will decrease. But when it first increase, the instantaneous value of VGS increases. Okay? If Vin increase, VGS increase. When VGS increase, that means the line that we are interested for VGS will jump one notch higher, because otherwise it's here. But then if VGS increases, we'll be selecting a higher line of ID versus VDS at the fixed VGS. But when it chooses a different value, let's say it was operating Q point here, it doesn't go up here. Okay, what it does is that it increases, it still intercepts a VGSQ, but it increases along the load line. So as Vin increases, the instantaneous value of VGS increases and Q point moves up the load line. A larger value of VGS means a larger ID and a smaller VDS. A larger value of VGS means a larger value of ID, because when it rises under this load line, when VGS rises, it means this Q point is going up. Okay, so which means as it rises, as VGS increases, ID also increases, but it's actually going against the increase of VDS, so it's decreasing VDS. So a larger value of VGS means a larger ID and a smaller VDS. So for a negative Vin, okay, the negative portion of the sine wave, because just now we said the input voltage would be rising, what happens? It goes down. Now when it goes down, the Q point will then have to follow the reduction of value in VGS, which means it will follow the load line and it will move down the load line. Okay, so a smaller VGS value means smaller ID and increased value of VDS as the Q point travels down the load line. But when you measure just here at ID, when VGS increases, you will find that ID also increases. Okay, still here. So for the FET to operate as a linear amplifier, the transistor must be biased in the saturation region, and instantaneous values of ID and VDS must also be confined in the saturation region, because if the small signal comes in, as VGS goes up and down, okay, which means that this Q point goes up and down, it must be careful not to go into the non-saturation region, because when it enters the non-saturation region, it does not act like a linear amplifier anymore. So the output signal must avoid cutoff, which is ID equals to 0, and must stay in the saturation region. If the output exceeds this limit, a portion of the output signal will be clipped, for example, and signal distortion will occur. This maximum range of output signal can be determined from the load line. Alright, now let's just review the notations used in the text. We have small letters with small letter subscript, or capital letters subscript, or small letters or capital letters with capital subscript. So take notes of the term used here. If it considers only DC constant value, or take a look as well, is it considering both, or is it just considering AC? Okay, so you can do just considering DC, you can do just considering AC, and you can do a combination of both. Okay, we're still at this example. Let's see what we want to do with this. Now let's have a look at VGS. VGS here, okay, is going to be, because now we have a DC source and an AC source, so this VGS here is going to be VGSQ plus Vin. So the notation here shows this. If I have a small letter with capital letter subscript, okay, it is actually a combination of DC and AC, where the DC is represented by the Q point VGSQ and the AC is represented by VGS, small signal analysis. Okay, so this is the DC component and this is the AC component. Now let's still have a look here. So you have AC component and DC component. Now if I were to take this expression of VGS and put it into this bracket, okay, it's going to be ID equals to Kn times VGSQ plus small signal VGS minus VTN squared. Oh, before I carry on, the purpose of this whole slide is just to explain to you, just in case you're wondering, who knows what is small. Okay, so if I expand this, small. If I expand this, ID equals to Kn of a quadratic equation, I can get this longer expression, which is an expansion of the quadratic equation. So this part here is DC ID. This part here is actually AC ID, and this one here, okay, produces undesirable harmonics, and it can be ignored. How do we make it ignored? We make it we can neglect it if VGS, okay, is much smaller than twice of VGSQ minus VTN. Okay, so if VGS can be ignored, then we say we qualify for the small signal AC analysis. So we have VGS less than 2 times the DC value of VGSQ minus VTN. So this is the condition for VGS to be considered small signal. Also from this expression, okay, especially if we look at this, we have this expression where ID is related to VGS by this device parameters and bias values. So we introduce the term GM, where ID is equals to GM VGS, and GM is rearranging this and referring to this gets 2Kn as a bracket VGSQ minus VTN. Alright, introducing transconductance parameter. Small signal ID is related to VGS by the transconductance GM. The transconductance is a transfer coefficient relating output current to the input voltage and can be thought of representing the gain of the transistor. So we usually look at GM as in ID equals to GM VGS, okay? And in the saturation region, from our previous findings, or if we were to differentiate the expression of ID with respect to VGS, we can get this expression where GM is equals to 2kn VGS Q minus VTN, or GM is equals to 2 square root kn IDQ. See, and if you look at this, even though GM is a transconductance parameter and GM is the value that from our DC analysis, actually what we want to find out is GM before we carry on with our analysis in the AC domain. Okay. So still the same graph, but now it's different. It's not ID versus VDS. It's not drain current versus drain source voltage. It's drain current versus gate source voltage. So you would expect if VGS varies, so would IDQ. So GM is the slope of the curve. If the time varying signal VGS is sufficiently small, GM is a constant. Okay, so if VGS is sufficiently small, GM is a constant, because when you look at something small, here all you see that it's like a linear line. Okay, so ID is linearly controlled by VGS. Now we can do some basic calculations here. Calculation from GM from given values, meaning from our question here, it has asked us to calculate transconductance when we have values of VTN, Kn prime, MW over L, as well as ID. Okay, ID is given in this case. So what do? We find the expression for Kn, okay, which is Kn prime over 2W over L. This is a standard expression when we do MOSFETs. Okay. So Kn is equals to 1.25 milliamp per volt square. And from here, because we know ID, we can assume that the transistor is biased in the saturation region. The transconductance is determined by this equation. From this equation earlier, so we have GM is equals to 2 square root Kn IDQ, which is equals to 1.41 milliamp per volt. Okay, so this is the value of the transconductance, and the value of transconductance can be increased by increasing the transistor W over L, and also by increasing quiescent drain current IDQ. Now that we know what small signal means, we know the values, the definition of the terms, and the parameters that are important for us as we enter the AC analysis, which is GM. Let's have a look at how to form the AC equivalent circuit. So it's not going to be different from BJT, except for the fact that the transistor is now not a BJT but a MOSFET. But the approach that we do DC analysis first, then do AC analysis, these are things that are common between the two devices. Okay. So the AC equivalent circuit is developed by setting DC sources equal to 0. So VDD becomes 0, VGSQ becomes 0. Okay. So this is what we have left with. We have the AC source Vin. The term VGS, capital subscript GS, is now VGS with small letters only, the same as ID. Okay, and VDD is connected to ground, so RD, one terminal is connected to drain but the other terminal goes to ground. So the small signal relationships are given with ID equals to GM VGS. We know that, right? ID is equals to GM VGS. VGS is equals to Vin. That's obvious as well, because this is just this loop. If I do a KVL, I'll get minus Vin plus VGS equals to 0. But mind you that these are AC analysis values, okay? And V out is equals to VDS minus IDRD. So V out, okay, positive is here. Okay. Therefore, the expression of V out Ohm's law across RD is going to be negative because the current is actually going out from the positive terminal. So I have here V out is equals to negative ID RD. So in the AC equivalent circuit, the DC voltage sources are equal to 0. Okay, these DC voltage sources are equal to 0. We say that the node connecting RD and VDD is at signal ground. Okay, so which means that VDD is not ground, VDD is power supply, but when we're doing AC analysis, it becomes ground, so it becomes ground to the signal when we are doing AC analysis for the AC signal. So NMOS small signal equivalent circuit, we assume for this stage that we are handling signal frequency that is sufficiently low so that any capacitance at the gate terminal can be neglected. Okay, there is a high frequency model, there is a low frequency model. We will be handling low frequency model. The input to the gate thus appears as an open circuit or an infinite resistance. So what you have here is like an open circuit. But this determines what VGS is because it goes into the output loop, which is which shows GM is VGS for this dependent current source with this arrow coming down. Okay. So the input to the gate thus appears as an open circuit. So it's just like having an infinite resistance at the input. Okay. Now let's draw a small signal equivalent circuit of the common source circuit example. The one at the top here, this is for the NMOS only. Okay, for whatever circuit that you have, as long as it is in saturation, you can use this circuit. But the one below here is this circuit still, which is VGS and GM VGS and R out. Okay, is representing this whole circuit is put here to represent the whole common source circuit example, which had RD and VN in the notation. So between the terminals drain and source, okay, between terminals drain and source, the transconductance parameter GM that we know is a function of the Q point. So GM is equals to 2 times square root Kn IDQ. Okay. And if we take into account finite output resistance for MOSFET in saturation region R out, which if you remember we covered this when we did device and DC analysis, most probably device. It is between drain and source terminal. Okay, between drain and source terminal. RD came because it was first connected, the other terminal was connected to VDD, but VDD became signal ground, so RD is also connected to ground. So R out can be found by this formula 1 over lambda IDQ. And to find gain, okay, how do we find gain from this circuit? It's just like BJT as well. What we do is that we find V out over V in. How do we find V out over V in? We can do Ohm's law at this end, okay, to relate V out with the values of resistance here. And then once we have that, we can find V in. Okay, we can find V in terms of VGS. Sometimes it's as simple as V in is equals to VGS, and then you go back to the expression of at the output loop, replace VGS so that in your term you have V out and you have V in. Therefore, you can rearrange to find the voltage gain AV to find to get it to be V out over V in. Okay, example of a small signal circuit, and we want to find gain. Okay, determine the small signal voltage gain here. Given DC values, okay, we have these are given values. Okay, so let's say VGSQ is 2.12 volts. Let's say VDD is 5 volts, and let's say RD is 2.5K. Now we have these transistor parameters where VTN is equals to 1 volt, Kn is 0.8 milliamp per volt square, and lambda is 0.02 per volt. Okay, so this is my to find the small signal voltage gain from this expression is my work. Okay, it's not that long because they've given us some nice values already, which is VGSQ, which you can find in ID. Alright, so you have a section just to do DC analysis. Then we check our assumption because it's the same approach. We just assume that it was an operation to start our calculation, but it may not be in saturation. So if it's not in saturation, we may have to attempt again for the analysis with a new assumption, which is if it's not in saturation, it will be in non-saturation, which is most probably going to be in triode. Okay, so you have here GM, because what you want to do is that you want to find small signal voltage gain. In order to do that, you have to be in AC analysis. In order to do AC analysis using this kind of models, low frequency models for MOSFET, you need to have this value GM. Alright, so let's have a look at the bigger picture here. Not the bigger picture, a picture that is bigger. Okay, so you have DC analysis, DC equivalent circuit, and because VGSQ is given, we can actually find ID directly. So if you assume unsaturation, IDQ is equals to Kn, which is 0.8, times VGSQ minus VTN, which is 2.12 minus 1, and square it up. So you have IDQ equals to 1 milliamp. And if we check assumption, we have Ohm's law. If we do Ohm's law here, it will be VDD minus VD times IDRD. And therefore, I can get the value of VD here to be 2.5 volts. But since Vs is equals to 0, therefore VDS is going to be 2.5 minus 0 volt. And you can have VDS set is equals to VGSQ minus VTN, because what we want to do is that we want to check our assumption. Okay, so now we're ready. We have done the DC analysis. We're ready for the AC analysis. Okay. So with AC analysis, because the channel length modulation parameter is given, we can find an actual value for the finite output resistance. Because most of the cases, if lambda is equal to 0, then R out is going to be approaching infinity, and you can actually just ignore R out. But in this case, it's given, so R out is 1 over lambda IDQ, which is equals to 50 kilo ohms. Now, I now draw the AC equivalent circuit, okay, of the transistor, which is between these terminals, gate, drain, and source, fit into the circuit. So RD, which was connected to ground, now goes to connected to VDD, now goes to ground. So I have here R out parallel with RD. Okay, and that is 50 kilo ohm parallel to 2.5 kilo ohm, which is equal to 2.381 kilo ohm. Okay, between these two. RD was a given value of 2.5 kilo ohm. Okay, so if I do, how do I get the voltage gain? It's the same thing as BJT. You do KVL at the output loop to get an expression of V out, okay, in terms of VGS, and then you find VGS at the input loop that relates VGS to Vin, and then you go back to the first term, replace whatever that has VGS with terms that has that came from the input loop. Okay, so in this case, this is what I got. I got an expression for V out, I got an expression for V in, and this expression for V in would be in terms of VGS. So I replace VGS in equation 1 by the value or the expression in equation 2. So I then get an expression of V out is equals to negative GM V in R out parallel with RD. And because this is V out V in, I can pull V in here and I can find this expression V out over V in, which is the voltage gain. And in this example, we got the voltage gain to be negative 4.26. Why is it negative? It means that the V out is 180 degrees out of phase to V in. Okay. So now, problem solving technique. In general, since we are dealing with linear amplifiers, superposition applies, which means that we can perform DC and analysis separately. So first, we analyze the circuit with only the DC sources present. Okay, find the Q point, and then replace each element in the circuit with a small signal model, including MOSFET. Okay, you have that model. Then you analyze small signal equivalent circuit, setting the DC source components equal to 0 to produce the response of the circuit to time varying input signals only.